With my company in Switzerland, we work on this new project in Lausanne. It's the extension of a library. You see here the University of Lausanne. This is the actual library here. That's been built in the 70s, around here. And now in 2018, you can see that the increase of students is quite huge. So the university needed to expand its facility. The project consists in adding a big space beneath the existing one. So this is the roof plan of the existing library, and beneath the library we create another library. What has to be said that all the spaces are interconnected, so it's all open space. That's why it has been very difficult to model and to calculate, as you will see in the next slide of the presentation. Here you can see the existing buildings on the left. That's all existing. It's a 3-floor actual library, and then a new addition building will be beneath the other one. So we have, in this situation, a lot of volume all open to the others, and we create more space in the next section. For the fire and smoke management, we will have to define several fire scenarios. And the first one will be on this floor here, another one on the same floor on the back, and then another fire here on the upper level. So we have stairs inside the building. So we'll describe a little bit how we did organize the smoke management of these spaces. Here you can see one of the biggest scenario is scenario 1 that I will explain more deeply. We have all this space here, it's all open. We can put fire here or here, and the places we can extract the smoke will be here on the top of the roof and in this space here. And the entry, the fresh air, can be done by here, and the back doors. One of the problems is this building here is existing, and the height of the roof is about 240 to 250 meters. So it's not high. And the rear part, it's a very huge space. You have more than 10 meters here. So you can see in the same model, you have problem with the smoke very quickly. The extraction of the smoke in this part here will be done by 48 smoke extractor here. They're big motors, but we can extract the smoke through this thin shades here in the roof. And the second most complicated scenario was the fire on the upper floor here, where you can extract smoke here and air coming from the front and the rear. So for the smoke management here was one of the scenario here, and all the possible scenario are shown in this picture. We have chosen to put in the model cellulosic and plastic mixed fire with 25 megajoule of fire load and 5% soot production in one scenario with 3 megawatts. And the small fire is more soot, but a very small power. That's the model of the building. You can see here in the front part the existing building and the adding building in the rear. One of the first errors on the study that we start with this model to study the problem, and we had a 13 million cells model. We needed 48 meshes to calculate it. It took every time 2 to 3 days on a HPC computer. That's we start with this model because we could do it. And then we realized that it was best to make another model, much simpler, with 3 million cells. And it took only 1 day on calculation. And so we start with the most complicated, and then when it was difficult to find good results, we made another simple model. So next time I will do first this model and then come back to this one to check the result. That's how we learn. For the evacuation modeling, it was quite easy because with the new building, we can add a lot of exits. It was very easy to exit this building, so it was not a real issue to exit the people. One of the constraints has been a very strong constraint from the client was the willingness to stop people going out of the library with the books in case of emergency. So they had put more than 3 minutes delay between the alarm and detection and the effectiveness of the alarm. So this has been complicated a lot, the evacuation possibility with this project. So then the process is quite standard with some pre-movement and movement parameters that we found authority. They tell us to use the RIMEA guide from Germany, and where you can find a lot of values. So we didn't reinvent the values. And then for the model for evacuation, we had to counterbalance the fact that we have to delay the alarm. We set two zones in the models. One with the witnesses near the fire, and a zone with non-witnesses people. So these people will get away from the fire without the alarm. And then when the alarm starts, everybody from this zone goes outside. So that's look the model is quite huge, but not so many people. So there are 2,000 people in this building. So for evacuation, it was not a problem. It's a little movie is going a little bit faster, so we can easily evacuate 2,000 people in less than 6 minutes. So this was not the case. So you see the first people that leave the zone, and in this zone, and not all of them go outside. The other people, they're not aware of the fire. So this in the other room, they're waiting. And then when the time is about 6 minutes, they begin to go outside. So it was not an evacuation issue for this project. The issue was for the smoke management system, because you had this existing building with very narrow ceiling. So that was the easy and the fun part of the project. So you see, it's quite easy to evacuate. What we have done, it was very interesting phase, is to develop some tools and post-processing tools that we have done internally. So for the authority, and to help us to convince the authority that it was safe evacuating this building with the smoke management system that we had planned, is to analyze the position. One of the options was analyze the position of the people in the time. So we developed a post-processing tool, which we used the X and Y position of the occupants versus time. And you can see on this is like accumulated density of the people during all simulation, and you can see on all the paths that the people have been using for evacuation. Another post-processing images is the available air set for the simulation. And you can see here is like the time the people are staying on this path. So as I said, these people are witnesses of the fire, so they will evacuate very quickly. So after 2 or 3 minutes, nobody is in this region. And then you can see that all the people start moving around 6 minutes. That was the most complicated thing in this building, that if you have a fire here, the smoke layer is difficult to stay with good condition. And one condition from the authority was to fix the extinction coefficient to 0.2. It's very severe. And you can see if you use this, people have the head into the smoke, so it's not good. But we thought that if you change this parameter, we can easily cope with 0.3 or 0.4 because the situation was good with the aid of the evacuation simulation too. So we developed another tool, and we can see here, and I don't remember if it's a Pathfinder output or we did it. So if I'm doing wrong, just correct me. We can see here the time where the criterion of coefficient of extinction is achieved. So you see that's only a few spots on the model where the conditions are degraded, and then the most of the surface is quite safe for the user. The last part of my presentation is a little discussion about this extinction coefficient that the authority in Switzerland they used to fix at 0.2. So here they consider if you have 0.2, there is no problem with the smoke, and you don't have to control all the other species. So you don't have to make a fed analysis. And for new projects, it's quite easy to cope with, but with existing building, you have so many constraints that is very difficult to achieve. So you can see we can put this line here for 203 or 0.4, and then prove with the FEE value that the security of the people is still good. That's as discussed yesterday too with other presentation. We can prove is if we cannot prove this extinction coefficient, we have to prove all the other species. And we can see that it's quite easy, and these projects are the value extracted from the model, that the extinction coefficient is the first value that is reached, and if you don't have this limit, you can go much further on the analysis and prove that it is quite safe, because we never reach this value here. So the discussion and the lessons from this big project, it was very difficult to keep a steady upper layer of smoke. So we first say we have to extract a lot of smoke in this project, and then the more and more we calculate, we said, no, maybe we have to reduce the volume and the speed of extraction because we are just mixing the smoke. So at the end, we were much closer to the natural air extraction than mechanical. And as I said, we start with a complicated model because we could do it. That okay, we can do it the complicated model, but we should have run a lot of trying with the simple model first, and then once we had a good solution, go to the complex model. So for me, it was not a good product for the company because we lost a lot of money, but I learned a lot, so I will do better for the next project. Thank you for your attention.
Thank you very much, Eric. I always like to hear people say that using our products is fast and fun, I think, as you said, or something, or easy and fun. Time for a few questions, comments, suggestions.
Yes.
So did you apply sprinkler system in your model? Because according to my experience, if you have sprinkler activated in the building, the situations sometimes disastrous. Is such a kind of buildings like this.
Yeah, we cannot have a sprinkler in this library because it's all books, and we don't want to put water and smoke in the books. So
that means you were lucky.
Yeah.
Very much. Thank you very much.
Yeah, there was just a fire at the library at Kansas State University on the roof, and they had to put it out with water from outside, but it soaked through and ruined all sorts of things, the historic room too. Other questions, suggestions?
Yeah.
I saw the size of your model. It was like 13 million cells.
Yes, it was quite huge, yes.
I guess my question is, what hardware configuration do you have to run that in?
We run the calculation on Sàrl core, the server, Sàrl core server, with 48 cores.
Okay. Okay, yeah.
So we have 48 meshes in this model.
All right, that's all I need.
It was quite fast. 3 days, I think it was quite fast.
Yeah, it's also possible to use cloud computing services and get virtual machines with that kind of level if you need. But
the problem, if we had found the good results faster, was not a problem. With this problem, we had spent 100,000 hours of calculations. So it was a lot, maybe 200 calculation of this project. Yeah. I didn't not shown because I finished the presentation yesterday and with not all the data from the office. Then was a luck to work with Parasim and Pathfinder. We can mix the results. I have not the images, but we had used to present to the authority the result of FDS on top of the Pathfinder results.
Anything else? Any other questions? All right, thanks again.
Thank
Eric.
you.